Hello mathematicians, welcome to the first of our calculus topics, where we're going to look at something called the derivative. Now, the derivative, which has as one of its representations this f dashed of x, is the gradient of the tangent to the curve y equals f of x at every point on the curve. Okay, so you might need to rethink about that one. At every point on the curve may have a different slope, and the slope of the curve at that point, which is the same as the slope of the tangent, is called the derivative. Now, there are a couple of trivial cases. Let's have a look at the most trivial to start with. So for a constant function, such as y equals c, where we've got a horizontal line, the derivative is the slope of that horizontal line, which we know is 0. If we have a linear function given by y equals mx plus c, then we know that the slope of that is m. So that's also the derivative. When we get to more complicated curves, then we need a different procedure for working out the slope. But let's just have a look at a GeoGebra of these. Now we'll just recap what we've already said. If we have the line y equals some constant, so I can change this value of c and my line moves up or down, but it's always horizontal. And in that case, the slope of the line is the same everywhere along it, and its slope is actually 0. Now I'm going to introduce this concept of a secant, which is just a short segment between 2 points on the line or on the curve. So the slope of the secant is the same as the slope of the straight line, and it doesn't really make sense to talk about the slope of a tangent just yet, because we know that a tangent technically, while it has the same slope as a curve, it only touches the curve at one point, and clearly that's not possible on a straight line. Now if we change the value of b so that we have a curve like this, which is a straight line, then we know that the slope of the straight line is the same as the slope of the secant. The pen is very sensitive today. If we look at the equation of our straight line just here, it's y equals 5x plus 0.05. We know that that means that the slope of the straight line is 5 and the y-intercept is 0.05. So the slope of the secant is also 5. But again, it doesn't make any sense to talk about the slope of the tangent. So now let's introduce a little complication, which is that we'll have a curve now which is a parabola. So this parabola is 0.05 as the coefficient of x squared. So it's concave up, and we can see that now when we look at point A, we can draw a tangent which touches the curve at one point and one point only. The slope of the tangent is 0.74, and that's actually the slope of the curve at point A. Now that's different to the slope of the secant that I've drawn in there at the moment, and particularly if I take point B further out, if I take point B further out, then the slope of the secant starts to vary drastically to the slope of the tangent. But if I bring point B down, this is very frustrating, if I can bring point B down so that A and B get closer and closer together, the slope of the secant and the slope of the tangent become closer and closer. And when they're on top of each other, then they're exactly the same. Now that will be an important point for later on. Now we'll just have a quick look at this GeoGebra as well. On this GeoGebra, what we're going to see is that the tangent is going to change its position along the curve. And if you look at the value of the slope of the tangent, you can see at the moment that it is a large positive number, 4.85, and we expect eventually that it will get smaller and smaller, and it's going to, as it gets to the top of this first bump here, it's going to equal 0 momentarily, which again is an important point for later on. So getting closer and closer, and at the very top of the bump, its slope is 0 as it passes through the horizontal. It now becomes negative, and it's getting to be a bigger and bigger negative. But if you watch about halfway towards the second bump, that negative will stop getting bigger and will start getting smaller again. Okay, so now we can see that process. So again, that point where it stopped getting bigger and started getting smaller will be important later on. Lots of important stuff to come. The slope of the tangent flattens out to 0 again and becomes positive on the other side of that lowest point. Okay, so these exercises are sort of trivial in the long run, but they're our introduction to calculus. So it says use the fact that the derivative of f of x equals mx plus b, our straight line, is, and we know that f dashed x is our shorthand for the derivative, so it is equal to m. So it's saying that the derivative of the straight line is the slope, and we know that the slope is the coefficient of the x. So we can just do it by observation. For example, f dashed of x here is equal to 7, f dashed of x here is equal to minus 3, f dashed of x here is equal to 0 because there's no term in x. That fits with what we saw before, that this is a horizontal line, f of x equals minus 4, so it has a slope of 0. Okay, write each function in the form y equals mx plus b, and then write down f dashed of x. So for what it's worth, if we multiply out, that'll give us 2x on 3 plus 8 on 3, y-intercept of 8 on 3, slope of 2/3, so f dashed of x equals 2/3. Now we'll see later on that basically we've just uncovered two rules of differentiation, two ways to find the derivative, and that is that if we differentiate a constant, so no x's, the answer is always 0. If we differentiate a term with a single power of x, the derivative is always just the constant in front of the x. Just a few warm-up exercises out of 7a.